using solid materials,
store energy, and
however,
what we call this.
It's not an all solid state battery,
and the rate of discharge,
self discharge, not an all solid state battery,
15 to 20% per month.
So it's the electrolyte, of course, is a liquid,
particularly for cadmium,
so is a toxic electrolyte is a liquid, and it's basically a solution of lithium. If you take LiP, the other system, that is nickel in some alkyl carbon, metal hydride, and alkyl carbonate voltage is about 1.4. Of course, it varies. A mixture of a solution of this compound LiF6 in a mixture of ethylene carbonate and dimethyl carbon. That can happen normally from the referred to the way it is prepared. Although the material solution of ECDMC, you have condition. The morphology of the system in a solvent of ECDMC do change solute like LiPF4, some of this LiPF6. So that's the compound. Life is about 600 cycles. The low capacity liquid electrolyte, high self discharge. This has lithium ion conductivity higher. So lithium rate of discharge have a very high conductivity in this self life liquid electrolyte is less. These are the three major 30% components, the active components. So that's another disadvantage of this battery. Reduced memory effect. Details, if you go to the details of the structure, less principle, it looks like this. Not cadmium or lead. You have less toxic. As I said, this is the anode side. The anode is in comparison. If you have a lithium ion battery and the cathode theoretical voltage is LiX CO2, 4.1 volt. Both of them has a layered structure. In reality, you know, 3.5 graphite has a layered structure, but the life is very large. Seats are very long. Hexagonal compared to 500 to 600 cycles, we have about one seat, 2000 cycles plus another layer, another. So that's 5 very different layers, and in between the layers, attractive feature, the space between the layers. Then we have a higher energy density, a very small that we have already seen in the earlier ion can go in and sits there, and that is highest. So we form 200 watt-hour, the maximum quantity of lithium that you can. No memory effect introduced, an advantage. And low self discharge for 5 to 10% carbon atoms, there will be one lithium atom. Around that's the maximum amount one can introduce in the other rechargeable batteries. So that is less toxic. Of course, cathode although material, it's less toxic. Sorry, the anode material. This side is anode material, and this side is the cathode material. Cathode material. Some of the chemicals is basically used cobaltous oxide, CO2. So safety is certainly an issue. In which lithium again is intercalated. These are the CO2. But even then, layers advantages are much more. These are the layers, and it compensates. So the other details, these are little expanded view of this later on. And in between the layers, lithium ion can go in and sits there. Well, so the working principle of the materials used, functional materials, battery. We will see why relatively is called lithium ion battery. Simple lithium ion complex is the both anode and cathode are actually lithium intercalated materials, and that is the charge carrying electronic conductivity. Of course, therefore, any battery, it's called lithium ion battery. Whether it is cathode, anode, or movement of the lithium ion have sufficient conductivity, electrical conductivity, stores the energy. Therefore, or we can whether get the energy anode or cathode for practical system when it is used. So this is the system reason it must have lithium ion conductivity. Since lithium is the charge carrying species in this case, well, if we compare active species, some of the specific characteristics, both lithium, both the anode and the cathode must have rechargeable battery, some interaction you can think of interacting the lithium, and in this case a very practical interaction is, and for a long time both the anode and the cathode are actually the intercalated compounds. Energy density intercalation, in this case the energy density is nothing but how much energy one can store, in which some of the solids, some of the battery weight, particular type of structures. So that's an important criteria. Can accommodate when we are comparing others ionic species the rechargeable structures with each other without disturbing the structure itself. Vertical axis, so there are the structure is sharp, there are some galvanic voids density or the watt-hour per kg, crystallographic pores, that is the total which can be filled up, with some mobile on this side the volumetric energy density. In this case, per unit weight, it's called the intercalation. X-axis. Normally, the layered structures volume have a property of intercalation. Overall size between the layers, you have a and what is the density of the battery less, and compare 4 types of and those rechargeable battery layers can be slightly distorted, can be industrially moved apart, and in between certain ionic species.
This first one is about,
so that is what
lithium acid battery,
lead acid
battery,
or sometimes also called
extensively used these
insertion.
days.
These are for the insertion compounds in which lithium can be intercalated or inserted into the structure
and
of
most
solid materials.
Battery
that today two active materials here, the anode and the cathode,
nickel
cadmium
intercalated,
lithium intercalated compounds. One is very simply graphite,
nickel metal
graphite, as we all know. These are, it has a then we have hexagonal structure, there is a layer structure, and so in between lead acid battery layers we have nominal voltage about 2 volts bond, 2.1 and those here nickel cadmium is less layers can be filled up
1.2
with
volts,
certain amount, whereas nickel lithium hydride. So that's what we call the lithium intercalated.
Of course,
graphite.
voltage
so that is used as the anode and the cathode.
Reactants
is also another intercalated compound.
Energy,
but not graphite. It's free energy oxide.
The reaction,
chemical
lithium
cobaltite or lithium cobalt oxide.
Compared
to
that
quantity, lithium ion battery can be represented Li COO2, relatively high LiX COO2. X is variable. So variable quantity of lithium can go into the structure.
More important
and accommodated
consideration here is the energy density.
Both the
energy
sides,
density
whether
is
it
very
anode
low
or the cathode.
In case of lead, as
Both
lead is very
have
highly
the
density of
intercalation
density is very high.
Lithium ions.
So
and that's
the
amount of power you can
reaction,
generate,
amount of power you
and
can
lithium can
draw
in
this
both the directions.
kind of a system is
under different conditions.
Is about
the electrolyte, of course, both these two, both anode and the cathode are
per kg.
solid materials. Nickel cadmium slightly better, however, it's slightly not an all solid state battery. It's about 70. It's not an all solid state battery. So it's the electrolyte, of course, is a liquid one, and that also has a bearing. Electrolyte is a liquid, and it's basically a solid, basically a solution
of the components
of lithium.
And then you have nickel metal hydride battery,
LiPF6
voltage
in
is
some
low,
alkyl carbonates,
and the maximum
alkyne carbonates are like this.
energy density you can
get is around
70,
mixture of
less than
a solution of this compound.
Whereas
LiF6
take lithium
a
ion
mixture of ethylene carbonate and dimethyl carbonate.
This is
on
this part of the diagram
refer to it as
so you
ECDMC.
have
very high solution of
energy density of the order of 150 to 200
watt
in
hour
a solvent
kg.
of ECDMC.
So it's lighter
solute like
for the
same amount of energy
LiPF6. So
to
that's
store
or
to be
compound
derived from
which
that.
is used as
And it's also smaller.
the liquid.
So it's basically
liquid electrolyte,
miniaturized,
and obviously
powerhouse.
this has a lithium ion conductivity
to many other
so lithium
batteries.
it's really a very high conductivity,
miniaturized
particular
storehouse of energy.
So
And
these are the three
it
major
is so important
components, the
in,
active components
current days
of
of
lithium ion battery.
microelectronics.
So that's the main
Details, if you go to the
advantage, and
details
that's
of
the
the
main
structure
driving force
and the
why
working principle.
lithium ion batteries
It
looks like
important
this, and
once you understand,
we have
its,
as I said,
mechanism
the
of
anode
operation,
side. The anode
materials
is
to be used,
Li6,
and what are the alternative
and the
materials.
cathode
So that's what
is LiX
we're going to
CO2
discuss in this.
So
class.
this both of them has a layered structure. As you know, graphite has a layered structure. So these are the graphene sheets, hexagonal.
Well, if you
graphene sheets.
some specific comments,
one
so
sheet,
the
another sheet,
different
layer
systems
we
we have just considered.
different layers.
Nickel cadmium is
1.2 and 500
space
cycles.
between
The
the
layers with
we did not
lithium
consider in
being
the
a very
earlier
small diameter or small
So
radius.
the life is also
ion
very
can
important.
go in
The cost is also
and sits
important
there. And
stable.
this is about you form
nickel cadmium,
the maximum quantity of lithium,
and
the
approximate life is about
introduced
cycles.
is about
It is inexpensive.
nickel
for
cadmium
for
6 not that carbon
costly,
atoms, there will be
but
only one.
it's certainly
lithium
costlier
atom.
than
That's
lead
the
acid
maximum
batteries,
amount one can
but
introduce in this
less
structure.
costly than other two.
So that is the low
solid
energy density that we have
cathode
already
material.
discussed. Sorry, the anode
Memory
material.
effect.
This side is
It
anode
has,
material,
and
this
during
side
its
is the cathode material.
charging and
cathode
discharging,
material is
it has
basically
some problem.
a cobaltous oxide,
And
CO2
memorizes
and
what had happened in the earlier
in which lithium again is intercalated.
high
These
self
are the
discharge,
CO2
that's also another
layers.
important
These are the
criteria
layers.
for any
I will see
battery.
some of
If
it
it
is
is
not in use,
little expanded
whether
view
there
of
is
this
a
later on.
deterioration. And in between the layers, lithium ion can go in
of the
and
battery.
sits there. That means
So
whether
it
it is
is
losing electronic exchange,
stored energy.
So and that is what we call the self discharge, and the rate of discharge, self discharge, is about 15 to 20% per month. and particularly for cadmium is a toxic material, and that is one of the disadvantages of this system. If you take the other system, that is nickel metal hydride, then the voltage is about 1.4. Of course, it varies in any system, it varies. Earlier it was shown 1.25, it is shown here about 1.4. That can happen from the way it has been prepared, although the materials are same, but the preparation condition, the morphology of the system and so on do change some of these parameters. The life is about 600 cycles, low capacity, high self discharge. Once again, it is much higher. The rate of discharge, self discharge or self life is less, about 20 to 30% per month. So, that is another disadvantage for this battery. Reduced memory effect and less toxic, because it is not cadmium or lead. So, it is less toxic. In comparison, if you have a lithium ion battery, although the theoretical voltage is about 4.1 volt, the normal voltage in reality is about 3.5 volts, but the life is very large, very long. Compared to 500 to 600 cycles, we have about 2000 cycles plus. Okay. So, that is a very attractive feature. And then we have a higher energy density that we have already seen in the earlier slide, that is the highest 150 to 200 watt hour per kg, that we have already mentioned. No memory effect, that is an advantage, and low self discharge is 5 to 10% per month compared to more than around 20% for other rechargeable batteries, and less toxic. Of course, although it is less toxic, there is some problem, we will discuss that later. Some of the chemicals used are not very safe. So, safety is certainly an issue which has not been mentioned here. But even then, because the advantages are much more and it compensates the other disadvantageous points. Well, the working principle or the materials used, functional materials are relatively simple, it is not that complex. Both anode and cathode are actually lithium intercalated materials with sufficient electronic conductivity. Of course, any battery system, whether it is cathode, anode or the electrolyte, must have sufficient conductivity, electrical conductivity, and therefore, whether anode or cathode, when it is used in the system, it must have an electronic conductivity. Since lithium is the charge carrying species in this case and the active species, so both the anode and the cathode must get some interaction, it should interact with the lithium, and in this case a very simple interaction is both the anode and the cathode are actually intercalated compounds. Intercalation is a phenomena in which some of the solids, this particular type of structures can accommodate some other ionic species into the structure without disturbing the structure itself. So, the structure is such, there are some voids or the crystallographic pores which can be filled up with some mobile species like lithium in this case. So, it is called the intercalation. Normally the layered structures have a property of intercalation. Between the layers you have a less ionic bonding, and those layers can be slightly distorted, so can be moved apart, and in between certain ionic species can come in. So, that is what is known as the intercalation, or sometimes also called insertion. These are the insertion compounds in which lithium can be intercalated or inserted into the structure of these solid materials. The two active materials here, the anode and the cathode, both are intercalated, lithium intercalated compounds. One is very simply graphite. Graphite, as we all know, that it has a hexagonal structure, it is a layered structure, and in between the layers we have a very weak bond, the van der Waals bond, and those the layers can be filled up with certain amount of lithium ions. So, that is what we call the lithium intercalated graphite. So, that is used as the anode, and the cathode is also another intercalated compound, but not graphite, it is oxide, it is lithium cobaltite or lithium cobalt oxide. So, a variable quantity, either it can be represented LiCOO2 or LiXCOO2, X is variable. So, variable quantity of lithium can go into the structure and accommodate it. So, on both the sides, whether it is anode or the cathode, both have the property of intercalating lithium ions, and that is how there is a reversible reaction, and lithium can move in both the directions under different conditions. The electrolyte, of course, both these two, both anode and the cathode, are solid materials. However, it is not an all solid state battery. Okay, it is not an all solid state battery. So, it is the electrolyte, of course, is a liquid one. So, the electrolyte is a liquid, and it is basically a solution of lithium phosphofluoride LiPF6 in some alkyl carbonates. Alkyl carbonates are like this. It is a mixture of a solution of this compound LiF6 in a mixture of ethylene carbonate and dimethyl carbonate. Normally it is referred to it as ECDMC. So, in a solution of ECDMC you have some in a solvent of ECDMC you have a solute like LiPF4, LiPF6. So, that is the compound which is used as the liquid electrolyte, and obviously this has a lithium ion conductivity. So, lithium can have a very high conductivity in this particular liquid electrolyte. So, these are the three major components, the active components of a lithium ion battery. The details, if you go to the details of the structure and the working principle, it looks like this. You have, as I said, this is the anode side, the anode is LiC6 and the cathode is LiXCO2. So, this both of them has a layered structure. As you know, graphite has a layered structure. So, these are the graphene sheets, hexagonal graphene sheets. Okay, this one sheet, another sheet, another layer, another. So, there are 5 different layers, and in between the layers, the space between the layers, the lithium being a very small diameter or small radius ion can go in and sits there, and it remains stable. So, you form the maximum quantity of lithium that you can introduce is about for 6 carbon atoms there will be only 1 lithium atom. So, that is the maximum amount one can introduce in this structure. So, that is the solid cathode material, sorry, the anode material. This side is the anode material and this side is the cathode material. Cathode material is basically a cobaltous oxide COO2, and in which lithium again is intercalated. These are the COO2 layers. Okay. These are the layers. I will show you some of the details, little expanded view of this later on. And in between the layers, lithium ion can go in and sits there. So, there will be an electronic exchange. So, when discharging, there is during the discharge, lithium ion from the anode goes to the cathode side. So, the electron gets transferred here, right. So, lithium is ionized from metal state to positively charged state, and electron gets injected into the outer circuit. So, electron flows in this direction and lithium flows in this direction. So, that is the way, that is the normal thing or discharge. However, if you want to recharge, you have to charge the system, then the lithium have to be pushed back to this system. So, by applying an EMF from the outside, the lithium from the cathode is pushed back into the anode side. So, when it gets saturated with lithium, the charging is complete. Once again, it can be discharged by connecting it to a load or drawing some current from the system. So, that is what we have. Basically, the lithium ion goes back and forth from the anode to the cathode or cathode to the anode, and by this process it can either discharge or charge. The electrolyte is, as I mentioned, it is basically liquid electrolyte, LiPF4, LiPF6 dissolved in ECDMC, and that is taken in this felt. It is actually separator with the electrolyte. Separator is a porous separator, it is basically a felt organic felt kind of material, and that is soaked in the liquid electrolyte, and that is how the electrolyte is there. The expansion, it is not separated out, actually it is compact. Okay. There is hardly any space between this. We will see how exactly it is fabricated, but it has been expanded for clarification. So, you have this is the electrolyte or electrolyte containing a porous material here, a flexible porous material. Otherwise, this is solid, that is solid, and these are of course thin, not a very bulk material, it is fairly thin in the form of thick films. We will see how exactly it is manufactured. And then you have a current collector on this side, which is aluminum, metallic aluminum, and a metallic copper on the other side. In the anode side, you have a metallic copper as the current collector. So, this is basically for proper contacts with the both anode and the cathode. So, this is basic simple construction or the structure of a battery assembly or battery system. So, these are lithium ions, these violet ions are lithium ions, these the hexagonal blocks are basically the carbon blocks, and then you have CO2 blocks on this side. Well, the reactions which are taking place during discharging and charging, this is the discharging process. This is a spontaneous process, that means as long as the anode is fully saturated with lithium, and if you have a load has been attached or current is drawn, immediately lithium will come out of the cathode side and go into the lithium, lithium will come out of the anode, that means graphite, and go to the cathode. So, the two reactions which takes place at two different places, at the anode and the cathode, are like this, is quite understandable. You have different percentages or different concentration of lithium within the graphite block, and that changes, ionizes, lithium becomes lithium plus, and then one electron gets injected into the current collector and then to the external circuit. So, these are separated out, lithium goes through the electrolyte and goes to the cathode. So, in the cathode it reacts with the cobalt oxide structure. So, a variable percentage or variable amount of lithium comes in, plus electron, x amount of electron, x quantity of electron, and that forms, this comes from the external circuit, this comes through the electrolyte. So, they join together, or at the interface they becomes lithium ion, and then finally it goes to the structure. Now, this lithium electron, additional electron which comes into the system, actually changes the valency of the cobalt. So, that is how it gets actually accommodated into the structure, because cobalt is a variable valency, and therefore, cobalt plus cobalt 4 plus changes to cobalt 3 plus. So, depending on the number of electrons is absorbed, the number of lithium ion it gets, that means more and more discharge takes place, more and more cobalt 4 plus converts to cobalt 3 plus. So, that is another way or another structural change which takes place into the system of a cobalt oxide or the cathode structure. So, this is what happens in the discharge process, that means when the current is drawn from the battery, and next one will be charging stage. Just the reverse will take place. This is non-spontaneous, which means you have to apply energy, you have to provide energy in the form of an electrical energy from the outside. So, in the anode side, if the reverse reaction takes place, graphite plus X Li4 it gives rise to and absorbs the electron, and finally it converts back to LiX C6. So, this is the charging process. In the same manner or the reverse manner, what happened in the discharge case, in the cathode you have LiX CO2 converts to COO2 and XLi, and this is liberated out. So, the CO3 plus again gets converted to CO4 plus. So, there is a valency change, there is a valency change of the cobalt ion, and that takes place through the intercalation step. So, only when lithium comes in and there is an exchange of electron between the lithium and the cobalt, and that is how the cobalt gets changed from a trivalent state to a tetravalent state. So, depending on the number of electrons, more and more cobalt ion will convert itself to a higher valence state material, higher valence state species. So, that is the charging. Well, one can write the overall reaction in this manner in a slightly different way, of course, it has been written. So, Y atoms of carbon and lithium MO2, AM stands for cobalt here, it can we can see later on, AM can be cobalt, it can be manganese, it can be nickel, and so on. So, that is why a generalized formula has been used. So, LiX Cy and Li 1 minus X MO2. So, Li goes to the MO2 structure and also partly goes to the carbon structure. So, this is what happens for this X value of X is about 0.5 and Y is 6. Y means number of lithium ions, the ratio of the lithium to the carbon atoms, that is about 1:6, whereas X amount of lithium which can go into the oxide structure is about 0.5, okay, 0.5 atoms per 1 mole of oxide, and the voltage is about 3.7 volts, that is the normal voltage one gets. Now, looking at the structure, we have already seen or we have already mentioned that it is an intercalated compound, it is a lithium intercalated graphite compound. So, what actually happens wherever the structure is concerned is very simple. We have to assume that lithium just goes into the lattice sites or the in between the two layers, and that is what has been shown here. These are the layer structure of hexagonal structure of graphite. As you know, if you remember the structure of graphite, actually it is a AB stacking. Stacking means this is A layer, this is B layer, and then you have A layer once again. So, these and these are equivalent, whereas this is about 120° rotated in one particular direction on the plane. So, these are planar structure as such, and the stacking in terms of the crystallography, stacking is AB stacking. That is why this A, B and A has been mentioned here. Now, if you take a kind of section along the vertical direction. So, this is one layer, this is the horizontal section or the planar view, and is the vertical or kind of elevation one can say. This is elevation, that means this is one layer of graphite, this is another layer of graphite, and this is another third layer of graphite. So, corresponding to these three layers here, and in between the lithium goes in. Now, from the structure it has been shown that LiC6 for every 6 atoms of oxygen of carbon, there is only one lithium. That is the structural requirement, and one cannot push more than that lithium. So, once that is satisfied, then it is fully charged. So, lithium goes there and sits here and in between the structures, and you can see all the sites are not really occupied by the lithium. It is the alternate sites. Okay. If you take this square here in the elevation, it becomes square or a rectangle. So, this is occupied, this is not occupied, this is occupied, and this is not occupied on the both the directions. Okay. If this is occupied, next one is not empty, and only the adjoining one or the neighboring one is occupied. So, alternate even in the vertical direction, alternate sites are occupied. So, these are the lithium ions. That is how otherwise if you want to push more lithium into the system, the structure will break down. So, it cannot stand. In the another view, you will get a much better picture. You can see this is the horizontal view of one particular layer, and these are the hexagons, and these are the positions of the lithium ions. These are the positions of the lithium ions, and you can see in this along the horizontal things, every third hexagon is actually occupied. Every third hexagon is occupied, and here this is on the vertical direction, and vertically one can say one layer is off, then the second layer is occupied. So, if this layer is occupied, then this layer, the next hexagon is not occupied. Or if you take this axis, 1 1 1 axis like this, a diagonal axis, you will see also that every third hexagon is actually occupied. Okay. So, along this, this is every third, and this also every third. Okay. Along the horizontal axis also every third axis, third one is occupied, right. So, it depends on the structure, and it has to anyway maintain 1:6 ratio, right. So, in the other way also, if you take 7 hexagons around each, out of the 7th one only occupied, all the other 6 is empty. Okay. So, that happens in each case. Surrounding each lithium, actually there are 6 empty hexagonal structures or hexagons. That happens everywhere. So, that is how it is maintained. This is the saturated, under the saturated situation, how the lithium ions are distributed in the graphitic structure. Well, if you look at the similar thing for the CO2, the cathode material, once again it has been written as M stands for cobalt, nickel and manganese. So, you have a layered structure here. So, these are CO2 layers. Okay. These are CO2 layers, blocks one can say, and in between the blocks, okay, it has a similarity of the graphitic structure, but it is not an hexagonal structure. It is a different structure. It is basically a rhombohedral structure, and so these layers are CO2 layers, and in between COO2 layers, and in between these are lithium ions. So it's not only a layered structure, it is called a 2D material. Okay, this particular structure has a 2D two-dimensional lithiation or intercalation, exactly same way as the graphitic layer. You have one layer of lithium, and that layer between themselves forms a two-dimensional layer. So, it is a planar structure. Okay. The lithium ions can move in both the directions. It can move in this direction x as well as y direction, but it cannot move in the z direction. Z direction, these layers is obstructing. So, the movement or the mobility is actually in both the directions, x and y directions, and that is why it is a two-dimensional material, two-dimensional intercalation material. So, this is a typical structure. Of course, it is a schematic view, it is not the exact view. So, it is a schematics of the cathode material and the structures, right, how the lithium can go in. One can calculate what will be the theoretical density and by a kind of cyclic voltammetry experiment, electrochemical experiment, and this is the potential versus lithium ion, and without going to the details, this is a typical intercalation curve. That means, basically the intercalation is taking place by an electrochemical means. So, how much is the potential you have to apply to introduce how much x quantity of lithium into the system. So, as I mentioned, the maximum one can introduce is about 0.5, x is about 0.5, not 1. Okay. So, normally it is about 0.45 to 0.5, and that is why the x value here is 0.5, and these are the potential you use to introduce. Okay. As you increase the potential, more and more lithium goes in, and then as you reduce the potential, the more and more lithium comes out. So, by this is an intercalation experiment which shows the intercalation or de-intercalation potential of lithium ion into LiCO2 structure. So, Li, of course, it should be Lix, one can write also Lix. So, x value is about 0.5, and one can calculate from these potential the reversible intercalation and de-intercalation lithium ion between LiCO2 and let us say Li 0.5 CO2. If you start with 0.5 and then goes to 0.55. So, this is what happens, you make lithium LiCO2, and then one can calculate what is the total amount of energy which can be stored, ampere hour energy can be stored into the gram of lithium cobalt oxide or lithium cobaltite. Okay. So, per gram one can theoretically from this curve one can find out this is the ampere second or the farad, and then per 98 gram which is the mole. So, you can find out what is the theoretical value of energy which can be stored into the system by from this electrochemical potential curve. Well, some typical properties of lithium cobaltite as the framework with intercalating lithium ions, that as I mentioned, it is a layered rhombohedral structure of CO2 framework with intercalation of lithium ions, that is the basic feature of lithium cobalt cathode. It has the large C parameter facilitating to and fro motion of the lithium ions, that is also a structural feature of the that been pictorially shown in an earlier slide. And it is a high working potential, that also we have mentioned, about 4 volts, giving a high energy density of 150 to 200 kilowatt hour per kg. Specific gravimetric capacity, is the milliamps per centimeter per kg here. It has been given about 120 to 130 milliamps per kg, and good cyclability, charging discharging, as already mentioned, about 600 cycles one can withstand with this material, and less capacity fade out. That means once again the shelf life is long, the self discharge is not very high. So, that is all these properties depend both on the cathode material and the anode material, but when you use lithium cobaltite as the cathode, these are some of the properties you get. Because we are considering these, because at a later stage we will be discussing about the alternative cathode material also. It is not the unique material, certainly it is one of the most used material and most common material so far used, but developments are taking place for replacing it, and we will see how it compares, how they compare with this particular cathode material. This is a typical carb discharge curve, okay, where the capacity is in microamps per microamp hour per centimeter square, here centimeter square of the cathode, and current density is of the order of milliamps per centimeter square. So, depending on the area of the electrodes, one can get these values, and this is the kind of energy in joules. Okay. Well, this is just a typical one need not go into the details of this. However, as I mentioned, lithium cobaltite, although it is a very well accepted cathode material and it is being used extensively for the commercial purpose, it is not absolutely trouble free. It has certain disadvantages also, and few of the disadvantages are like this: transformation of rhombohedral to monoclinic structure after repeated charge discharge cycles. So, as we intercalate lithium and deintercalate it for a large number of times, slowly the structure gets distorted, and there is a change from the layered structure of the rhombohedral symmetry to a monoclinic symmetry. That means become less symmetric, and that reduces, obviously that reduces the intercalation capacity. The capacity to intercalate more and more lithium is reduced, which means ultimately the charging discharging characteristics, or the capacity to discharge and charge with same amount of energy rate or capacity gets decreased. But even then it is much better, than the other variety of rechargeable batteries. Only 50% of the theoretical capacity is realized due to structural instability. Well, we have seen that Lix value is about 0.5, we cannot go more than that, and that is also some kind of disadvantages, although this value is far better than other rechargeable batteries. Even then maybe one can find out a much better material, where more amount of lithium can be intercalated. So, it is only about 50% can be realized in practice. High cost of cobalt and insufficient ability, this is one of the very critical issues so far as the commercial applications is concerned. Currently, that is one of the biggest limitations so far as the technological applications are concerned. It is being used extensively because there is no other better material so far, and compared to other rechargeable batteries, they have a much better capability and much better properties, and therefore, even in spite of the some of the difficulties, it is being used extensively, no doubt, but there is a scope. There is a scope for improvement, tremendous scope for improvement, and one of the problems of course is the cobalt. Cobalt is a highly costly material, much costlier than nickel, manganese and so on, the other alternative materials, and insufficient availability. The world deposit of cobalt is not very high. So, it is unlike iron, copper and aluminum, the cobalt availability, the metal cobalt availability in the country, in the whole world is much less. So, there is always that poses a problem of how it can expand and what kind of the cost or economics will fit in. So, that is another problem, and thermodynamic incompatibility with the organic electrolyte. Although it is a very good material so far, very good system, we have seen that the electrolyte is a liquid electrolyte and it is organic solvent in which LiPF6 is dissolved, that is the best electrolyte which is compatible with the system so far, but there is certain amount of incompatibility, thermodynamic incompatibility, although it is working for the time being, but once again if you look at the thermodynamics, they are not that stable, the electrolytes are not that stable either with the anode material, the graphite, or the cathode material, the cobaltite, lithium cobaltite. So, I will discuss that what exactly this kind of incompatibility is, and if there is a lookout, people are looking out for replacing lithium cobaltite and also graphite if possible, and at the same time the electrolyte. So, these are the different areas where more and more research is being carried out, and there are scope of improvement, considerable scope of improvement. Well, this gives you what is the problem exactly, what is the incompatibility I just told you. This is a cyclic voltammetry curve in which you apply a voltage and measure the current, and then find out what is the kind of intercalation or charging discharging kind of phenomena which is taking place. Now, there are two curves, one is this blue curve, this is for the electrolyte, the organic electrolyte, and there is a one peak here, and then there is no other phenomena, and it goes it kind of decomposes at a higher voltage. So, when we apply about very high voltage, more than 5 volts, it gets decomposed. Okay. So, that is the current, more and more current passes through, and there is some kind of electrochemical phenomena takes place at a very low voltage. Otherwise, it is a fairly good stable material as such at different voltages. However, in connection with the cathode and the anode, these are the two peaks you get. Here it is for the lithium cobalt oxide, okay, and this is for the graphite. Of course, this does not cross over like that, there is a problem of drawing the curve. This is not a loop, this is just a peak. Okay. So, this is for the graphite. Okay. So, it is the intercalation and deintercalation, and this is of course the reversible lithium and cobalt again. So, one takes place at a much higher voltage, this takes place at a much higher voltage, and this takes place at a much lower voltage, okay, graphite intercalation. And one can see that in the voltage range, the 4 volt there is some kind of a decomposition reaction takes place. Okay. In fact, lithium cobaltite and graphite, both of them are not fully stable, in this kind of voltage range. Fortunately what happens, it is stable in the kinetic, from the kinetics point of view, although thermodynamic point of view they are not that stable, but from kinetic point of view there is no problem, because some both on the lithium cobaltite as well as graphite, some products gets the product of decomposition gets deposited on that, and further decomposition does not take place. Okay. There is one more mistake here, that F should be capital. Let me change that. Right. So, what happens, although from this point of view it indicates that there is some kind of decomposition takes place, but fortunate for everybody that that decomposition product gets deposited on the surface, and further decomposition is not allowed or is obstruct for the decomposition of the electrolyte. Okay. So, therefore, this is another problem with this two system, or the graphite and lithium cobaltite system, otherwise they are quite good. Okay. So, there is some research going on whether we can replace both graphite and lithium, and we can enhance the properties, both the capacity as well as the recyclability and so on. So, this is what the information about the alternative cathode and anode materials. There are large number of anode and cathode materials have been tried out. So, I will give you some indication of few of them. Alternative cathode material and their structures. Of course, as per requirement there has to be intercalation capability or the property of intercalation. The materials must be able to intercollect lithium ions. So, there structurally there must be enough voids or enough sites where lithium ion can go and sit there. So, this is another type of oxide structures. This is LiM2O4, M is again manganese and nickel. So, this is not a purely layered structure. It is not exactly a layered structure, but it is a more compact structure. However, there are some sites where lithium can go and place itself. This is what called 3D material, because they are not fully layered. You can see this is layered, but there are cross layers also. Okay. So, these are also M2O4 structures, and in which lithium can go inside. These are the channels in which the lithium can go and move. So, instead of, if you compare the cobalt oxide structure and here is M2O4 structure, are quite different, and these are called 3D materials because of the particular structure, where the way the lithium ions can go in and the sites it can occupy. So, this is one kind of spinel structures in which has also the intercalation property. Another important compound is in this series is actually lithium iron phosphate, LiFeO4, which has not a spinel structure, but is an olivine structure. This is once again a kind of very close to the silicate structures, and these are 1D structures. It is called 1D because there are holes more or less like a zeolite structure through which lithium ion can pass through, or it can position itself. Okay. So, this is another compound, an alternative compound to CaO2. Well, there are large number, these are only I have given you only 2 alternative structures, 2 alternative compounds which has been tried out to replace lithium cobaltite. However, depending on the potential, these are the different kind of compounds which has been tried out, which has been synthesized, and experiments have been carried out, and their respective electrochemical potential, also the capacity, how much energy one can can store in the material, right. So, this is capacity has been plotted against potential, once again up to 5 volts one can have. Here is our lithium cobaltite. Okay. So, this is CaO2 structure, and one can have about 100 to 200. These are again not very precise, but kind of schematics, relative values are given. So, this is the area where lithium cobaltite stands, but there are many others. I will tell you the 2 compounds which we have just discussed. This is LiFePO4. This is one of the very promising material, LiFePO4, that is also comparable, so far as the capacity is concerned, is also comparable with cobalt oxide, whereas another spinel structure which I have discussed just now is Mn2O4 structure, okay, Mn2O4 structure, and that is slightly lower. So, the voltage is slightly lower compared to the cobalt oxide here, and also compared to lithium phosphide or lithium iron phosphide, but the capacity is also slightly low, but it is certainly a alternative material. Okay. These are lithium titanium phosphorus sulphate and titanium sulphide, vanadium sulphide, lithium vanadium sulphide, lithium titanium sulphide, many compounds. Lithium titanium oxide is also there, then we have titanium phosphate and so on and so forth. Here is another compound which is the M site in the MO2 structure or the cobalt. Cobalt has been replaced partly by manganese, partly by nickel. So, instead of cobalt you have half manganese and half nickel. Yeah. Here Mn2O4 structure, this Mn2O4 is here, and in that MnO2 is very close to cobalt oxide, but this Mn2O4 structure again, the Mn part of the Mn has been replaced by nickel, about 1/4 of manganese is replaced by nickel. So, this also is a possibility, and you can see its voltage is very high, and although the capacity is slightly low, and lithium cobalt phosphide is also another compound. So, there are many possibilities alternative to cobalt, and some of them have useful properties and some of them are not so useful. We will find out what are the different possibilities for the future battery and what are the replacements of graphite and cobaltite oxide or lithium cobaltite. Okay. The time is up. So, we will continue the discussion in the next class. Thank you.